Well, I trust you had a great break. We're in the final sprint here. I guess you just got through your final round of midterms on the week before Thanksgiving. Hopefully, they seemed like they went well. I didn't have much feedback from people. Not sure if there's anything we need to discuss here. No. Yes? No, 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 no. So the presentations are in now. They should have been in. I haven't checked with Matt as to see what's arrived or not. So I think a peer review note went out, ostensibly signed by Matt, but I sent it out. So it should be on your mailers this morning from midnight tonight. And so 15% of the grade is a kind of a peer review, so you get to comment on your co-members in terms of putting the stuff together. And so that's due sometime. So do that. We'll try and get that in for everybody, and then account for the grades. And so all we have left now is this week, 3 classes in class, and the final week of classes are 3 midterms that were in line with Penn State Faculty Senate policy, can't be worth more than 10% overall. So the other midterms are worth 20% together, all 3 tests. So these will be worth 10% together. So that's a requirement of Penn State, actually in your best interests, to protect you from having faculty who put 50% of your grade in the final weeks of classes, and you have 5 deliverables for 5 classes like that. So that's what we have left. I think the presentation grades will probably be in finals week. For those of you who have conflict exams because you've missed a class with notes, which aren't very many of you, those will be in the final slot. So there is a final slot booked for this test, but that's not for the vast majority of you. It's for those who have to catch up on something that they missed in the midterms on the way through. So that's where we are, I think. So the final midterms or finals in next week are the review sessions posted. It's been posted for, I think, for more than a few days now. And it's not cumulative, it's just the last 3 sessions. So it covers 11.3, which is pipe networks, 12, which is open flows, external flows, I guess, and this week, which is open channel flows. And so those are documented in the same way. So there is a pipe network question, there is an external flow question, and there is an open channel flow question, one of each. So noted in the same way as it has been for all the other things. Those could be my most watched videos, I guess. I'm not sure whether the people who don't turn up to class actually watch these recordings or not, but they're there regardless. So that's where we are. Right? Anything else that we need to discuss? Questions, comments? Yep.
You said that the last set of exams are going to be happening during class week or during the finals week?
During class week, next week. So a week today will be the first of them. Yeah. And there is no final for if you haven't scheduled a conflict exam, which yeah. So I've had some questions. Why is there a final scheduled for this class when there is no final? So that's the utility of it. Okay. Okay. So, hearing no other business, perhaps we'll continue with this, right? So this is for those of you. Well, the Appalachian region is known for whitewater boating. I guess it's seasonal, usually with snow melt, although we don't get much snow these days. So it's usually in the springtime and on rivers that are dam controlled. This is West Virginia, a bunch of rivers, Gawley being one of them, where people do these things. And open channel flows, I guess, different from our other flows that we've seen, you actually have a free surface, right? Top of the water. External flows have been enveloping, either all the way around an airfoil or Baumgartner dropping out of an airplane, out of a capsule taken up by a balloon, but they've been all enveloping. And the difference with open channel flows is that it has a free surface which regulates the behavior. And in concert with this, before we get into it, one last video, I guess is this, is that because there's a free surface, the flow can organize itself in a binary in two different ways. So this could be, you see that upstream there's a flow that's shallow, and downstream below this hydraulic jump, as it's called, the flow is deeper. From continuity, you would know that the upstream flow is much faster than downstream flow, and because they have to have continuity, if you draw two vertical lines in each location, one here and one here, then the flow, if it's steady state, has to be constant, equal at each of those two gateways. And so the upstream flow has to be faster because it's going through a smaller area, and the downstream flow has to be smaller. And actually, you've done something like this in one of your examples on when we did mass conservation of mass, and one of you tried to do it using Bernoulli and found out that it didn't work. And it doesn't work with Bernoulli's because as you go from upstream to downstream, the energy is not conserved in the system, because it violates one of the things in Bernoulli, and that is that you have all these vortices which are really eating up the energy in the system, just like pipe flow and viscous drag on pipes on the inside and on objects on the outside for external flows. The essence of those problems is understanding the losses within this system. And so when we deal with so-called rapidly varying flows, rapidly varying in depth from upstream to downstream, or it could be the other way, going from a deep upstream to a shallow downstream with the same ramifications for the velocity changes, then we have to account for energy losses in the system. So that's kind of the essence of what we might want to talk about here. So that's, I didn't want to do that. I will put that on hold so it doesn't do anything strange for us. So, the essence of these flows are exactly that. Don't know what that is. Don't need to comment. So we'll talk about open channel flows. Maybe, although it doesn't have it written on here, maybe it's useful to give a recap before we talk about those. And because we've talked about a bunch of individual things. And so I've showed you these plots before, but let's do it again. Let's talk about the commonalities between pipe flow, external flows, and open channel flows. And so the commonalities are, if I do this, I'm going to draw three diagrams like this. And you've seen the segmented plot that I had before in three columns, but for pipe flow. So in all cases, this is Reynolds number, which is equal to a velocity times a density times a characteristic dimension divided by a viscosity. Same in all cases. This, for pipe flow, we have essentially P1 minus P2. We can do it by writing Bernoulli, or the energy equation, in terms of upstream and downstream. We have this is equal to sum of HL plus sum of HL. So these are major and these are minor. And you know what these are. These are a friction factor is equal to, head loss rather. Head loss is equal to a friction factor, length of pipe, hydraulic diameter of pipe, and V squared over 2G. And minor losses, I guess I shouldn't be doing them so low because I'm moving into this. Minor losses are a loss coefficient times v squared over 2g. So they have the same parameters here that they're working on. We end up with this typically because upstream and downstream of a pipe, typically the diameters are the same, and so the cross-sectional areas are the same, and so V1 equals V2, and so it cancels out in Bernoulli. But this is the velocity that's actually in the fitting or in the pipe, and we know that these Moody charts look like this. And we understand, hopefully, the characteristics of those charts, and that is that in this part, this is, in all cases, this is laminar, this is turbulent, this is a function, friction factor is a function of Reynolds number, or reciprocal Reynolds number, and this is increasing relative roughness. So these are larger numbers and these are small. You'll remember it's a log scale. Log scales on both axes. And these are for different values here. And so importantly, friction factor is constant for all of these. And therefore velocities and losses are proportional to, are due to density. San Francisco, truck at San Francisco International gets pushed off because you're killing the momentum of the stream that hits against its side. So it's really the density that's causing the push on that. I guess that's really for this one here, but it's the same. We talked about open flows. We're interested in the force that's applied to the body. We don't care about the flow field. Pipe flows, we're interested in the force that's applied to the flow field that slows it down, but it's the same effect. And this is also, as we know, this is kind of an Euler number, which is an Euler number is equal to a pressure change over rho v squared. So that's exactly what this friction factor is. And so in this zone here, friction factor is proportional to viscosity. Friction factor, or head loss is I guess probably head loss, right? It's not really friction. Head loss. Viscosity, head loss is proportional to density in the system. Just the way it works out. You remember that if you play around with these, you get a term over here which is v squared. You have a term over here which is v because there's a velocity already included in Reynolds number, and one of the velocities drops out, and so you solve for that system. When we looked at external flows, bless you. We look at drag and weight. Essentially, of course, that's a d, curly d, not a diameter. And we know that we can define a coefficient of drag or a coefficient of lift as CD is equal to squarely d divided by a half rho v squared, a I think as well, right? D over a, yeah, must be. So, and we made the point that this d over a term is really a pressure, right? A force divided by a planiform area, the area that this sphere sees, which would just be its pi d squared. This is don't want to confuse things, but this is d in terms of diameter. And we have exactly the same behavior that we see here. I think probably we have something that looks like this. We get some interesting little behaviors in terms of anomalous responses here. But this also is that, what is it? It's also C over Reynolds number. And this is different curves for different shapes. And so the same thing. Coefficient of drag is controlled by density. Coefficient of drag is proportional to viscosity in the laminar regime. And we have all the same behaviors. It's just like a Moody chart, but this Euler number now is really a drag coefficient or lift coefficient, the only difference being that a drag coefficient is in the direction of the airflow and a lift is perpendicular to it by definition. And so we have this. And so we know that if we're in the turbulent regime, we just have a constant value for this drag coefficient. And when we solve for it, we solve for v squared, so we have to square root it. If we're in this regime, the drag coefficient is a function of Reynolds number. And so because Reynolds number contains a velocity, one of the velocities drops out when we do the drag calculation, and we end up with something being a function of velocity. And so that's the way that we solve them. So finally, for open channel flows, it's kind of part of this continuum, is that we have a thing called a Manning coefficient, as we'll find, which is also a Reynolds number, which is also an Euler number. M-A-N-N-I, well, that's terrible writing. M-A-N-N-I-N-G, name for Mr. Manning, and also Mr. Chezy, in a different way, the Chezy equation, which is N. And we'll find out that the behavior is like this again. And this is kind of increasing relative roughnesses. We won't call it relative roughness, but it's going from a glass line channel to a concrete line channel to a soil line channel. So increasing roughness of the side. And what we'll find out is that for open channel flows, getting pretty good at drawing things almost. So open channel flows are defined in terms of a depth of flow, which we'll call y, and a velocity. And I didn't write the equation down, but we'll see it soon enough, the so-called Manning equation. So what we'll find out also is that for even modest widths of channels, we're almost always in the turbulent regime. So I didn't mention it before, but we assume always for fittings, the fact that KL is typically a constant de facto means that we're over in this side of the curve, and we're assuming that flow within those fittings is turbulent. If we look at open channel flows, we'll find out that the laminar regime doesn't exist. Almost all flows are turbulent, and so the values of this coefficient change from small numbers, Manning is small, to big numbers as you change the different makeup of the stuff you're flying at. So that's kind of the continuum of these three things that we've done in the last portion of this course. Looking at pipe flow, looking at external flows, and open channel flows. They all kind of conform to the same behaviors. They all are kind of pseudo-Moody charts. They have a laminar regime and a turbulent regime. It's made a bit more easy for us in this case because we have only a turbulent regime to deal with, but it's actually made a bit more complicated because flow can organize itself either a fast, shallow flow or a deep, slow flow. and we have to choose between those somehow. And so we have to work out a rationale to do that. So that's what we'll spend a bit of our time doing. And so I'll bring that back up, but the other thing that you've seen that relates to this, I don't know if it's on, probably won't be able to find, yeah, I did find it. So you've seen this figure before. It might not have meant anything to you or much to you the first time you saw it, but it should mean something to you now, in that we have these three different geometries. If we're doing dimensional analysis, then we have these three requirements of geometric similitude, kinematic similitude, and dynamic similitude. Geometric similitude means that the models have to look the same in some way between prototype and model. Kinematic similitude means that we have to be running at the same Reynolds number between the two models, because that makes our flow regime look the same. And if that's the case, then if the Reynolds numbers are the same in the model and the prototype flows, then if the Euler numbers are the same, then we can calculate what the pressure is that's making it flow, or the pressure is that's applied on our airfoil, or the pressure drop that is applied in our pipe between upstream and downstream. We can get that from the remaining requirement of dynamic similitude. So we don't have to derive any equations. We could do a bunch of model studies and get that out of it. But this is it follows the same path. So the same goes for what we're talking about now. These charts, the Moody charts we look at, are just saying that you need to be present at the right Reynolds number. And so we make sure that we're sitting at the right Reynolds number through all of these. And if we're at the right Reynolds number, we know what the friction factor is, or we know what the drag coefficient is, or we know what the Manning's number is. And so that's all we're doing to be able to do this. So what we'd like to do for these, again, too much whiskey, is actually Drambuie last night. What we're having, we'd like to be able to calculate what the velocities, the flow rates are within our system. And so we need to be mindful of two things. One, that we can have flows organized in two ways: fast, shallow flows, or deep, slow flows. And also it allows us to reorganize in terms of the depth of flow. I guess that is the main one. Okay? So that's the recap. So what we're going to talk about. So we'll talk about flow classifications. And so we'll talk about gradually varying flows. There's an intermediate one, and then there's rapidly varying flows. The hydraulic jump that we just saw is a rapidly varying flow from upstream to downstream. We'll define, when we talked about non-circular section pipes, we talked about hydraulic diameter, which we used to represent the diameter of our pipe. But we can also define things in terms of what we'll find out as a hydraulic radius. We'll talk about, I guess, that was on. Uniform flows was the first one, gradually varying flows and rapidly varying flows. There is no third one. And we'll talk about the Chezy or the Manning formula, which is where the depth as you go downstream doesn't change. Upstream and downstream are the same, such as you do the calculations in 99% of your the things that you'd want to do. And then, not today, but next time, we'll talk about gradually varying flows, where the depth changes with distance downstream. And we'll also come back to talk about things like wave speeds, which we talked about in our second class, about tsunamis. And wave speeds have something to say about open channel flows, because a wave speed of a wave in water, if you have a river flowing downstream, and if you look at the wave speed emanating from dropping a pebble in, that's carrying information away from that impact to the further reaches of the flow. If the flow downstream is flowing faster than the wave speed can travel upstream, there's no way that information can be transferred upstream. And so it defines some different forms of flows. So I'm going to use my old notes, the former notes for this. So I think the main issue two issues in pipe flow. One is that you have a free surface. So that's an extra wild card in terms of the fact that it could be a shallow fast flow or a deep slow flow. But the other thing, I suppose, is that there is no pressure difference between upstream and downstream. If you try and, this might be flow within a pipe, but if you have a pressure difference between upstream and downstream, it will just short circuit it by going through the air, and therefore it won't be able to hold much of a pressure difference between upstream because it will be transmitted in the air above the water. And so the pressure difference is only given by the depth change, the change in pressure with depth. And so it's really the only driving force is gravity that's pushing it downstream. Just like rolling a ball down an inclined slope, the only thing that's making it move is gravity. We can define behavior in terms of two numbers. One you know very well, which is Reynolds number, which we'll talk about. We've alluded to the fact that that's important because of the Moody-like Manning charts, but also Froude number, never quite sure how to pronounce it. And the Froude number is the ratio of inertia to gravitational forces. And you'll remember that this number on the bottom, gravitational acceleration times the length, if you take the length as the depth of flow, this was actually the wave speed of a surface wave traveling, a tsunami, for example, is given by this. So this is actually the ratio of the velocity of the flow within your pipe or open channel to the wave speed. And it signals as to whether information can be passed upstream, which we'll talk about, which I think is kind of a cool idea. So we've made the point already that we think we're always turbulent. In open channel flows, we define something called the hydraulic radius, which by definition is just the cross-sectional area of flow divided by the wetted perimeter. Just as a hydraulic diameter was the cross-sectional area of flow times the wetted perimeter. The wetted perimeter was the circumference of the pipe that it's flowing by. But of course, in open channel flows, the wetted perimeter would only be the wetted part of that flow, but the area would be the full area. By definition, this is the definition of hydraulic radius. I still don't understand why, if you put the terms in for this, the area, if it was fully wetted and circular, this would be pi r squared, and this would be 2 pi r. So this is actually equal to r over 2. You don't get the actual radius out of it if you put these terms in for circular section, right? This pi r squared and 2 pi r would be if this section was absolutely filled. So I imagine you could fill this section, imagine a little air gap at the top. That would still be an open channel flow because it's being driven by gravity. But the hydraulic radius doesn't work out to be the radius of the pipe when you put those in. The hydraulic radius is actually equal to the hydraulic diameter over 4, just by rearranging this term here. And so if we put in the hydraulic diameter into our Reynolds number equation, which is all I'm doing here, then you end up with 4 times RH. And so different from pipe flows and external flows, the characteristic dimension that we choose is the radius rather than the diameter, hydraulic radius. And this is the hydraulic radius. And so for that reason, since they're a factor of 4 different, then our usual transition from laminar to turbulent happening at about 2000, a Reynolds number of 2000, happens at 500. And so I guess, I see you writing things down. I'll come back to that, but I'll just put on these figures. So this is, as you recall, is 2000. This, as you recall, is 2000. This is 500. And this is velocity times density times hydraulic radius over viscosity. This is velocity, density, diameter, or some characteristic dimension divided by viscosity. So that's an important difference in these. So this breaks at 500. And the reason it breaks at 500 is just by definition that we choose to use a Reynolds number which includes a different length scale. And it's the so-called hydraulic radius. Okay. So, what else? I let you take it on trust, but haven't really shown it to you that we're always in the turbulent regime. We could work out what that is just by assuming some parameters for this. If we work out a Reynolds number for a stream 10 feet wide, a foot deep, flowing at 2 feet a second. I know I said we'd never use English units or imperial units, but the Reynolds number, 2 feet a second. The hydraulic radius is the area. The area is 10 square feet, 10 by 1. And the wetted perimeter is 1, 10, 1. So this is 12. And this is dense, this is density of water. This is viscosity of water in English units. And if you go through that, you end up with a big number, much bigger than 500. So by definition, we're definitely on the right-hand side of our Manning chart, and therefore that's why we will define flows purely in terms of a friction factor, which we call N, which is a Manning coefficient. So that's it. So the flow types that we'll deal with are kind of classified here. Uniform flows are the easiest, which we'll deal with today, for which we can use the Manning charts. And they're characterized by the fact that the upstream and downstream depths are the same. They're on an inclined plane. And so these depths are actually measured perpendicular to the basal section, so they're kind of an inclined Y. But the beds are so shallowly sloped that it's probably not important to make that distinction. Gradually varying flows are where they change from an upstream value depth to a downstream value, and they're not the same. And rapidly varying flows are the case where they change in an extreme way. So for this one, upstream is this deep, downstream is this deep, and we have all this commotion going on in the middle, which is our energy loss, which, of course, if you're using Bernoulli, we said in viscid flows, no viscosity losses, no head losses due to viscosity, no vortices, so no losses due to vortexes, isothermal, incompressible, and steady state were the requirements. So we'll look at steady state flows for these. So we'll look at all of these. Today we'll look at uniform flows, which are the case where upstream depth, so the coordinate system for this is depth is vertical, along flow depth length is x, which is this. And so when upstream depth doesn't change as you go along, you have a so-called uniform flow. Mathematically, it's just given as dy dx equals 0. And so for gradually varying flows, this gets progressively larger, still not very big, as you'll see here, much less than 1. And here, much bigger values for rapidly varying flows. We'll look at steady state flows only in our system. So in other words, rate of change, if you take a snapshot, it doesn't change. So that means that if you take a side-on snapshot of this, if you look at this now, or if you look at it in 10 minutes, it's still all of the way along this flow, it looks the same, although obviously the particle of water, or the molecule of water that existed here, is no longer here at the later stage. So we know exactly what steady versus unsteady means. And the difference between these uniform and non-uniform flows are kind of epitomized here. Non-uniform flows is basically the depth of flow upstream and downstream changes. And we can also define the slopes of other variables in the system as we go downstream. So you'll see here that this is the bed slope, and we can define the bed slope as equal to, this would be delta z over x. This is just the slope of the bed, which is obviously, put a ball bearing on a flat slope, it doesn't move. Put it on an inclined slope, the further inclined, the faster it will go. And so you can imagine that flows are the same. Hydraulic grade line would be, this would be the elevation head. This would be the pressure head, kind of, right? So if you wanted to get the pressure at this point here, it would be equal to YU times unit weight. So this is really the pressure head. So elevation head, pressure head, and velocity head. This is measured perpendicular to the bed, but it's so shallow that it's irrelevant as to which it is. And I guess for uniform flows, the point is that the hydraulic grade line and the energy grade line are all the same gradient, and the upstream and downstream flows. And of course, they have to be that because if this depth here is the same as this depth, then the velocities here have to be the same. And so v squared over 2g upstream and downstream also have to be the same as well. Not so when we deal with non-uniform flows, that these individual slopes, the energy grade line, hydraulic grade line, and the bed slope can all be different from each other. But this is the one that we're going to deal with today. So what else do we need to think about? Let's not worry about this figure on this equation on the right. We were interested in the fact that we have flow within it. We know that we have a free surface of flow area, wetted perimeter. So this is the area, and the wetted perimeter is this for a bed. Side-on view, upstream and downstream. I guess the reality is that in these systems, if you want to go fast in a river, go down the middle of the river. Don't go at the bank where it's dragging against the side. Just like in pipe flow, if the section was fully filled, we had zero velocity at the boundary of the pipe, and we have a maximum velocity in the center of the pipe. In open channel flows, you'd expect to have the zero velocity at the perimeter all the way around, and the maximum velocity where it's unconstrained in the middle. Like in pipe flow, we assume for these calculations that we do that the flow is of uniform velocity across the section. And so the area of this red trapezoid or prism, let me use my special marker. This area here would be exactly the same area as here, just like we did for pipe flow. Oh, an artiste, n'est-ce pas? And so that's our assumption. So we don't really care the fact that there are changing velocities in the flow field, because really what we want to calculate is that a volumetric flow rate is equal to a velocity times a cross-sectional area, typically, right? And so to do that, we need an average velocity, and this, of course, would be the average velocity across the section here. And we know that there are shear forces added at the sides, and they're probably not uniform, but we perhaps don't worry about that too much either. Oh, running out of time. Too much chatter. Okay. So let's figure out how to analyze these. You'll remember that conservation of momentum says that the forces, sum of forces in the x direction is equal to mass flow rates times sum of velocities in the x direction, right? From our dim and distant past. This equation here is exactly that. This is mass flow rate times the velocities. And you remember that we do it so that we sum the forces. So the forces upstream would be this trapezoid here, which would give us F1 acting downstream. We have the forces downstream acting upstream, which would be F2, the area under this trapezoid. And so we could work out, we don't really know what these are, but we could guess. If we write this, the velocity upstream and downstream from what we've said have to be the same because it's steady state. Flow volume in equals flow volume out. So by continuity, upstream velocity and downstream velocity have to be the same because it's the same cross-sectional area or depth, y1. So this depth is y1, perpendicular to the slope. And so since these cancel out, then we know that the forces have to cancel out. We could imagine that the forces would cancel out also by knowing that the depths are the same and that these distributions of forces are just the same as a swimming pool, the static change in pressure with depth. And so we know that this ideally on the left and right side has to equal 0. So what we could do is we could do a force balance between the upstream and downstream. We know from this that the sum of the forces are equal to 0. So if we take the forces acting in the positive x direction, which is just backwards, is it? I guess in this direction. So if we resolve with positive x in this direction, F1 is positive, F2 is negative. We have a shear force acting on this base. I won't draw it very well here, but you can imagine a little shear force here, which is tau. And of course, if I draw the side perspective view of this channel, then this perimeter almost did it. The perimeter is just this length here, right? And the area is this area here. And so the shear stress is a stress that's applied on the perimeter, and the length of this section here is L. And that's the same as this length here. I know. So the only thing that matters out of this is the final equation that we get out of it, by the way. So this is the shear stress times the perimeter times a length. So this is an area that the shear stress is applied on. Oh, sorry, yeah. Probably don't want to do an A, uppercase A. The area would be the area of this channel, right? If I did it this way, in other words, it would be this area here and on this side here and on the bottom as well. So, and the only force that's pushing it down is the component of the weight. So the weight is equal to unit weight times the cross-sectional area times the length. So the cross-sectional area times the length is the volume times the unit weight, if you can see this here, is this. So this is equal to area times the length times the unit weight. And the component of it acting downstream is if the bed is angled at theta, then this angle in here is theta, and so the component of that that's acting downstream in the same direction as the forces acting upstream and downstream is W sine theta. So this is just a free body diagram. Cut the stream upstream and downstream, leave it there, look at all the forces that are acting. There's a force acting downstream and upstream which must balance from what we said earlier. And so the only forces remaining are the shear on the bed and the weight that's driving the flow. They must be equivalent to each other. That's what this expression is here. We can substitute the fact that sine phi and tan of phi for small angles is equal to delta, what do we call it? I called it delta z before, over L. The height drop between, so this is, as you go downstream, this would be delta z. We must be running out of time, I think. Yeah, not quite. And so we can make these substitutions. We have a value for W, which we know. We have the gradient of the bed, we have a wetted perimeter, and we have a length over which it occurs. And so we can rearrange this in terms of the definition of hydraulic radius, which is merely by rewriting this as this term here is this. This is this. Yeah, so it's the same equation. And so by realizing that the area divided by the perimeter is by definition the hydraulic radius, we can substitute this. So this is the end result of this. Driving the flow, unit weight, and the hydraulic radius. So this is a balance between the shear resistance resisting the flow and gravity that's driving it through this unit weight and this slope. I'm not sure we talked very much about the Darcy-Weibach equation, but you can see that this is basically the loss factor for fittings, right? KL times V squared over 2G is the head loss in a fitting. And so this is kind of what this is. If we equate these two to each other, this is just saying that there's some coefficient that defines exactly how big this shear force will be that's resisting flow within the fittings, or in this case within the open channel. Then if we can define KL, then we can say how much drag is applied to the flow for a given gradient of the bed. And so if we equate these two equations and go through manipulating them, we have a V squared term in here. So if we rearrange the equations in terms of V squared, so we equate these two equations, actually it's this equation here. So we have hydraulic radius, unit weight, slope of the bed is equal to this term. If we rearrange it in terms of V squared, we get a bit of a complicated equation. If we realize that this term includes our loss coefficient, which is going to be a number, depending on whether we have a glass-lined tube or a soil-lined tube or a glass-lined ditch or a glass-lined or a soil-lined ditch, then we can take this outside. And C is the so-called Chezy coefficient, if you speak French, or Manning coefficient, if you don't speak French, I suppose. One from the UK, and one from England, and one from France. And the punchline here is this. This is all we need to know. The rest is just pain for this morning. You need a bit of pain on a Monday morning. Is that we can define the velocity as a function of hydraulic radius of the open channel, the gradient of the bed, and some coefficients. And this might be the only equation in this class where it's dimensionally defined. In petroleum engineering, every single equation you use, you have to use the right units to get the right units. So for us, this has to be in metric. It gives us a velocity in meters per second as a function of hydraulic radius in meters and a bed slope in terms of length over length. I guess that's dimensionless. This coefficient kappa is 1 if it's in SI units, and we use the Manning coefficient, which is just a number. If we want the volumetric flow rate, we just multiply, realize that Q is equal to a velocity, average velocity times the cross-sectional area, which is what this is here. And if we want to use English units, then we have to use kappa is 1.49, and the units are in feet and seconds. So hydraulic radius is in units of length, and so it would be in units of feet. And that's it. And, well, we'll probably, yeah, fine. So maybe we'll start from there next time. We have plenty of time to do this. So that's it. So we'll talk about the end part of uniform flows next time, and then we'll move on to gradually varying flows, which is actually more interesting than this. Thanks very much.